If you walk into your garage, um, pick up a rough, dark piece of heavy-duty sandpaper, and then look at a flawless red ruby set into a royal crown.
Right.
Chemically speaking, you are looking at the exact identical thing.
Yeah, it's the ultimate chemical identity crisis.
It really is.
Because, I mean, we tend to rely on basic physical categories to navigate our lives safely, you know?
Yeah.
Like, hard things are for building, shiny things are for jewelry.
Invisible things are for breathing.
Exactly.
Yeah.
But when you zoom down to the molecular level, those intuitive categories don't just blur, they completely flip.
Which is wild. So, welcome to another deep dive, everyone. Today, we're taking you on a journey into the hidden architecture of literally everything around you.
And we've got some really unique source material today.
We do. Our map for this is a set of translated excerpts from a really fascinating Czech chemistry textbook. We're looking at a chapter covering, and excuse my pronunciation, the Dvoufokové sloučeniny.
Which translates to binary compounds.
Right, binary compounds. And specifically, we're focusing on oxides.
And just to set the stage for you quickly, a binary compound simply means two elements bonded together.
Just two.
Yeah, just two. In this case, we are talking about oxygen pairing up with just one other element from the periodic table.
And the mission of this deep dive is to explore how that incredibly simple recipe, oxygen plus one guest, creates the most extreme contrasts in our physical world.
It's a very stark contrast.
Oh, totally. I was reading through this source material, and it honestly doesn't feel like a dry academic text at all.
No, not at all.
It reads like this bizarre hybrid between, like, a hardcore wilderness survival guide and a high-end jeweler's catalog.
That's actually a great way to put it, because the overarching theme here is the uncompromising transformative power of chemical bonds.
Yeah.
When you take two elements and combine them, you aren't just mixing their traits together like red and blue paint making purple.
Right, you're not just averaging them out.
Exactly. You are forging an entirely new entity with its own distinct rules. I mean, these simple binary pairings have the power to sustain human life, or
end it in minutes.
end it very quickly. They build ancient civilizations and they tear them down. So today, we are decoding that manual.
Okay, let's unpack this. There is probably no better place to start than with the compounds that are just intimately familiar to us.
The ones we breathe.
Right. The gases we produce just by existing, the carbon oxides. We're going to look at how a single microscopic extra atom of oxygen dictates whether you're enjoying a refreshing afternoon beverage or facing a lethal invisible threat.
Let's start with the heavier of the two, the one with that extra oxygen atom, carbon dioxide, or CO2.
So the textbook notes that CO2 makes up about 0.03% of the air around us.
Which doesn't sound like much.
No, but we create it with every single exhale. It is also the primary byproduct of what chemists call the perfect combustion of fuels, like coal and natural gas. Like
Yep.
when there is plenty of oxygen to go around during a fire, you get CO2.
Perfect combustion is really the defining condition here. The carbon atom gets fully saturated.
Meaning it has all the oxygen it wants.
Pretty much. It forms stable bonds with two oxygen atoms, creating a molecule that is essentially chemically satisfied.
Okay, so I was struck by this laboratory experiment outlined in the text that completely changed how I visualized this gas.
Oh, the flask experiment.
Yes. So the instructions describe taking a flask and mixing 10% hydrochloric acid with a piece of limestone.
Which is calcium carbonate.
Right, calcium carbonate.
Yeah.
When those two interact, they vigorously bubble and produce pure carbon dioxide gas.
Standard chemistry lab stuff so far.
Standard stuff. Then the book says to insert split like a little wooden match into the flask, and the flame dies instantly.
Because of the CO2.
Right. But here is the wild part. You can literally pour the invisible gas from that flask into an empty second flask.
Like pouring water.
Exactly like pouring water. It stays inside the new container, pushing out the normal air, and if you lower a match into that second flask, it gets extinguished too.
The physics of that demonstration really force you to stop thinking of a gas as just like empty space.
I know, it makes you imagine CO2 as this invisible, heavy liquid pouring over the lip of a glass.
Because it is denser than standard atmospheric air and completely non-flammable, so it behaves like a heavy blanket.
Yeah, it just obeys gravity and sinks to the very bottom of whatever container it finds itself in.
And by pooling at the bottom, that heavy blanket smothers the flame by physically pushing away the oxygen the fire desperately needs to burn.
Which leads right into an incredibly practical safety tip from the textbook.
Oh, the well tip.
Yes, it poses this question. Why is it highly recommended to lower a lit candle into a deep well before you climb down into it?
Well, it comes down to basic fluid dynamics, and frankly, it is a matter of life or death.
Seriously. If CO2 is seeping into a deep well from the surrounding soil, it won't float up into the sky. It pools at the bottom, just like water filling a bucket.
Yep.
If you lower a candle down on a rope and the flame suddenly dies, you've hit the surface of an invisible lake of CO2.
And if the candle suffocates, so will you.
Exactly. And to bring this into modern reality, this isn't just an old-timey well problem.
No, not at all.
Today, brewers working around enclosed fermentation vats or people in poorly ventilated basements, they face this exact same hazard.
It's a real occupational danger. But if we look at the macro scale, the source text highlights the profound dual nature of CO2.
Right, because on a small, controlled scale, it's totally harmless.
It's what we use to carbonate lemonade and beer. I mean, that sharp fizz on your tongue is carbonic acid forming from dissolved CO2.
We freeze it solid to make dry ice.
Exactly. But when this exact same heavy gas accumulates to the lower layers of our atmosphere, it stops acting like a refreshing fizz and starts acting like a thermal blanket.
The greenhouse effect.
Correct. And the mechanism here is that CO2 molecules are virtually transparent to the shortwave radiation coming from the sun.
So the sunlight passes right through.
Right, but they absorb the long-wave infrared heat that the Earth tries to radiate back into space. The molecules literally vibrate and trap that heat.
And the textbook impartially lists the resulting mechanics of this, right? Like the melting of glaciers, rising sea levels, and the potential flooding of low-lying areas.
Yeah, it just lays it out. It illustrates how a substance that is totally safe in a soda glass becomes a massive planetary variable when the scale shifts.
So that's carbon dioxide. 2 oxygen atoms fully satisfying 1 carbon atom.
Now let's look at carbon monoxide, or CO.
Just 1 carbon, 1 oxygen. The text explains that this gas is born from imperfect combustion.
Right, the starved fire.
Yeah, if a fire's burning but starved of air, meaning there simply isn't enough oxygen to go around, it turns out CO instead of CO2.
Which is why you find it in cigarette smoke and heavily in car exhaust.
Exactly, and the text notes that European cars, for instance, face really strict emission limits for it.
Because automotive regulators focus heavily on combustion efficiency to prevent this.
But I struggle to wrap my head around this part. If CO2 and CO are constructed from the exact same ingredients, carbon and oxygen, why is CO so immediately lethal?
It's a great question.
I mean, we exhale CO2 constantly without any issue. How does one missing oxygen atom turn a simple molecule into an assassin?
It all comes down to the underlying valency, or the electron structure of the molecule.
Okay.
Imagine CO2 as a fully locked puzzle. All the pieces fit, it has smooth edges, and it doesn't need to interact with anything else.
It's happy.
Right. Carbon monoxide, however, is a puzzle missing a crucial piece. Because it only has 1 oxygen atom, the carbon has unused bonding capacity. It is a jagged, incomplete molecule that is violently desperate to find stability.
So it's actively looking to hook onto something to complete its structure.
Precisely. And the physiological mechanism detailed in the text is incredibly insidious.
What happens?
Well, when you inhale carbon monoxide, it enters your lungs and interacts with your red blood cells. Your red blood cells contain hemoglobin, which acts like a microscopic delivery truck for oxygen.
Right, moving it around the body.
Under normal conditions, oxygen binds to the hemoglobin, rides through your bloodstream to your brain or muscles, and detaches where it's needed.
Makes sense.
The carbon monoxide's jagged, desperate structure binds to that hemoglobin with an affinity that is over 200 times stronger than oxygen.
Oh, wow. So it doesn't just steal the seat on the delivery truck. It literally welds itself to the seat.
It absolutely refuses to let go. So even if you are gasping in a room full of otherwise normal air, if there's a sufficient concentration of CO, your red blood cells are fully occupied by carbon monoxide.
So you can't process the oxygen you're breathing.
Right. Your brain and organs suffer from acute cellular oxygen starvation.
And what makes it terrifying is that the text points out CO is completely colorless and has absolutely zero odor.
None.
You literally cannot smell your own cells starving.
Which dictates the textbook's urgent first aid protocols. I mean, you can't just open a window and hope the victim recovers.
Because the CO is still stuck to their blood.
Exactly. They require immediate removal to fresh air and artificial respiration to forcefully introduce enough pure oxygen to gradually displace those stubborn CO molecules.
before severe, irreversible brain damage occurs. So one missing oxygen atom and a harmless byproduct of respiration becomes a cellular hijacker.
It's chilling.
It really is. Now, it's easy to think of oxides only as invisible gases born from breathing or simple fires.
Sure.
But let's pivot to the harsher gases produced by heavy industry and the burning of much lower quality fuels. We're moving to the sulfur and nitrogen oxides.
The industrial breath of the planet.
Yeah. These compounds illustrate how chemical toxicity can be both a severe environmental hazard and a highly optimized tool for human civilization.
Let's dive into sulfur dioxide, SO2.
Okay, so our source explains this gas is produced when burning lower quality fuels.
Specifically brown coal.
Right, which can contain up to 2% sulfur or heavy heating oils. And unlike carbon monoxide, sulfur dioxide makes its presence known immediately.
Oh yeah, you can't miss it.
It is colorless, but it has a pungent, stinging odor that causes aggressive coughing fits.
Because it actively attacks the mucous membranes in your respiratory tract.
The textbook includes another lab experiment that is just perfectly grim. I kind of call it a botanical crime scene in a beaker.
A botanical crime scene. I like that.
Well, they instruct you to place some fresh green moss inside a glass vessel.
Okay.
Then you take a small piece of sulfur on a wire, ignite it, and lower it into the glass, sealing the lid.
So it fills up with smoke.
Right. As the sulfur burns, it fills the container with sulfur dioxide gas. Under the influence of that gas, the green moss rapidly changes color, dies, and just withers away.
It's fast, too.
And the textbook's conclusion is blunt. Sulfur dioxide is toxic to organisms. Under its influence, moss perishes.
What's crucial to understand is the why behind that withered moss.
Why does it die so fast?
When sulfur dioxide encounters moisture, whether that's the damp surface of a moss leaf, the wet lining of your throat, or rain clouds in the atmosphere, it undergoes a hydration reaction.
Meaning it mixes with the water.
Yes, it combines with water to form sulfurous acid. That acid literally destroys cellular structures from the outside in.
Oh.
And on an industrial scale, this is the exact mechanism behind localized acid rain.
Which is awful. But here is where the textbook drops a brilliant twist.
Yeah, this part is fascinating.
Humanity looked at that beaker, looked at that dead moss, and decided to weaponize that exact destructive mechanism for our own benefit.
The toxicity is a dual-edged sword.
Completely. The text jumps straight from "this causes acid rain" to "here is how we utilize it."
Right.
We use the cellular destroying power of SO2 to disinfect wine cellars. We use it to bleach materials like straw and cotton, literally employing the harsh chemical reaction to strip away pigments.
It's incredibly effective.
We even use it to sanitize beehives and protect fruit from mold. Like, we took a hazardous industrial byproduct and turned it into an agricultural guardian.
It really speaks to the pragmatism of chemistry. But, the sulfur oxides aren't the only volatile actors here.
No, they aren't.
The nitrogen oxides, or NOx, provide perhaps the most striking contrast in how subtle molecular tweaks yield vastly different realities.
The textbook mentions nitrous oxide, N2O.
So that's 2 nitrogens, 1 oxygen.
Right. It's a colorless gas with a surprisingly pleasant, sweet odor. In fact, you've probably encountered it at the dentist. It's laughing gas.
Used widely in medicine as a mild anesthetic.
Exactly. A completely benign, medically invaluable compound.
But if you alter the recipe, removing 1 nitrogen and adding a second oxygen to create nitrogen dioxide, NO2, the reality shifts dramatically.
It's like night and day.
The textbook describes NO2 as a dark brown, highly poisonous gas with a suffocating sharp smell.
You transition from a pleasant, pain-relieving therapy to a toxic brown cloud capable of severe respiratory damage.
Just by adjusting the ratio of oxygen to nitrogen.
And furthermore, our source notes both of these gases serve as intermediate stepping stones in the massive industrial manufacturing of nitric acid.
Right.
That just blows my mind. Like, you're navigating a chemical plant where one pipeline holds a medical anesthetic and the pipeline right next to it holds a lethal brown cloud.
Both serving the broader industrial machine.
Yeah.
This is also why modern vehicles are equipped with catalytic converters. They sit under your car right now using rare metals to chemically force those harmful nitrogen dioxides back into harmless nitrogen and oxygen before they ever leave your tailpipe.
Because nature doesn't deal in approximations.
No. The ratios dictate the poison.
It's all about the ratios. Now, so far, we've only explored gaseous molecules that are light and volatile enough to float away, choke a room, or trap global heat.
Sure.
But when oxygen finds a heavier partner, the resulting molecular weight and lattice structures ground them. They don't float into the atmosphere.
They fall to the earth.
And they form the literal bedrock of human civilization. We are moving from the invisible gases to the solid builders.
So this is where chemistry becomes architecture. The solid oxides.
Let's examine calcium oxide, CaO. To manufacture this, you don't just mix two liquids in a test tube.
No, it requires a lot more energy.
The text explains you rely on a massive industrial kiln. You take raw limestone calcium carbonate and subject it to intense thermal decomposition.
You basically blast it with extreme heat.
Right, to literally shatter the chemical bonds, driving off the carbon dioxide gas and leaving behind pure calcium oxide.
And humans have been performing this exact process for thousands of years. It forms the basis of ancient masonry.
But I'm genuinely stuck on the mechanism here.
How so?
Well, if I walk outside and pick up a piece of limestone, it's completely inert, like I can skip it across a pond.
Sure.
But after we bake it, the resulting white solid is explicitly warned by the textbook to be a strong caustic that will severely burn human skin.
Yes, it is highly dangerous.
Where does that latent, violent energy actually come from?
So that baked rock is now what we call burnt lime or quicklime.
Okay.
The intense heat of the kiln forcibly ripped a stable CO2 molecule out of a happy relationship. What remains, the calcium oxide, has a massive energetic void.
So it wants something back.
It is fundamentally unstable and desperate to restore its molecular balance by bonding with water.
And human beings are mostly water.
Exactly. Our sweat, our eyes, our respiratory tracts.
Oh.
When quicklime touches moisture on your skin, it violently reacts to snap those new bonds into place. This is an exothermic reaction.
Meaning it creates heat.
It releases a massive amount of heat energy, causing severe thermal and chemical burns. It is literally boiling the moisture on contact to stabilize itself.
That is terrifying.
It is.
But despite being a flesh-burning hazard, it is completely non-negotiable for modern building.
Because when you intentionally feed water to that burnt lime in a safe, controlled environment, it becomes slaked lime.
Which is different.
Very different. As our source material points out, slaked lime is the crucial binding ingredient in cement. It's heavily used in glass manufacturing and metal refinement.
So the danger is the utility.
Exactly. Our safest, strongest, most enduring structures, the foundations of our homes and the skyscrapers of our cities, are fundamentally held together by highly reactive caustic chemistry.
The danger is exactly what makes it strong. But, if calcium oxide is the hyperreactive hungry builder, the text beautifully contrasts it with another solid oxide.
Silicon dioxide.
SiO2. This is the stoic survivor of the chemical world.
It provides the perfect counterweight. Silicon dioxide is a fully satisfied, incredibly tight molecular lattice.
You interact with it in nature as the mineral quartz or as the core component of sandstone and granite.
Very common stuff.
Right. And the textbook outlines its properties. It is exceptionally stable. It is a solid substance that is remarkably difficult to melt. And it is completely impervious to water and most acids.
It doesn't violently react with the world, it just endures.
It just sits there.
And that endurance is the backbone of our infrastructure. Silicon dioxide is fundamentally sand.
It's just sand.
We utilize that sand to create mortar, we use it as a structural aggregate in concrete, and we melt it down to manufacture heat-resistant materials and everyday glass.
It's the indestructible counterpart to the reactive lime.
Right. Calcium oxide provides the chemical binding energy, and silicon dioxide provides the eternal unyielding structure.
Together, they literally pave the modern world.
They really do.
So, if calcium and silicon oxides are the practical, heavy-lifting builders, the final oxide on our list proves that nature's utility can also be jaw-droppingly beautiful.
Yes.
We are talking about aluminum oxide, Al2O3.
A truly fascinating compound, primarily because of how wildly its physical presentation can vary depending on just microscopic factors.
The textbook introduces aluminum oxide by noting it occurs naturally as an incredibly hard mineral called corundum,
Right.
and also as bauxite, which is the raw ore we mine out of the earth to refine into everyday aluminum metal.
So your soda cans and airplanes.
Exactly. Bauxite is the muddy starting point of modern aviation and packaging.
But bringing it back to that twist you mentioned at the very beginning of our deep dive.
Oh, yeah. The textbook casually drops an absolute mindbender here.
It really is.
It discusses a dark gray rough stone called emery. If you have some heavy-duty sandpaper out in your garage or like a grinding wheel on your workbench, you are looking at emery.
It's a brutal industrial abrasive.
Used to grind down hard metals and strip away rust.
It is purely functional, designed to destroy whatever it rubs against.
Right. But chemically speaking, that dark gray sandpaper material is the exact same compound aluminum oxide as the precious gemstone sapphire, which is brilliant blue, and ruby, which is deep red.
It perfectly captures the blind mechanical nature of chemistry.
I cannot get over that. The grit on a piece of sandpaper and the crown jewels of an empire.
Identical.
They are the exact same. How is that possible?
Well, it comes down to the crystal lattice structure and microscopic trace impurity.
Okay.
Pure aluminum oxide is clear. But if a few atoms of chromium sneak into the crystal structure while it's forming deep underground, the entire crystal turns deep red, and we call it a ruby.
Just a few atoms.
Just a trace amount. And if trace amounts of iron and titanium slip in, it turns brilliant blue, and we call it a sapphire.
But the underlying binary compound is identical.
Identical. The chemistry doesn't care about our human concepts of financial value, rarity, or beauty.
Right, it doesn't know it's a ruby.
It simply builds the structure based on what atoms are present. The exact same molecule that you use to harshly grind down a rusty pipe in your driveway is also carefully cut, flawlessly polished, and set into gold rings for royalty.
It forces you to look at everyday objects with a completely new level of respect.
It really shifts your perspective.
Let's recap the journey we've been on. We started with translated excerpts from a chemistry textbook about binary compounds. Just the simple rule of oxygen pairing up with one other element.
And look at the spectrum of reality that one rule creates.
It strips away our assumptions about the physical world. I mean, by pairing oxygen with carbon, we get the refreshing fizz in a cold drink, the invisible thermal blanket warming our entire planet, and the silent, odorless killer lurking in our car exhaust.
And by pairing it with sulfur or nitrogen,
we get cellular-destroying toxic clouds that we brilliantly repurpose to sanitize our agricultural harvests and relieve pain in dental chairs.
Right.
And when oxygen grabs hold of heavier elements like calcium, silicon, or aluminum, it drops out of the sky.
It becomes solid.
It turns into the caustic cement that binds our skyscrapers, the indestructible sand in our glass, and the stunning red rubies on our fingers.
I want to leave you with one final detail, actually, tucked away in the footnotes of our source material, that pushes this into a planetary perspective.
Oh, what is it?
The text briefly mentions that iron ores minerals like hematite and magnetite are also oxides.
Iron oxides. We're talking about rust.
Exactly. Oxygen is so fiercely reactive, so determined to fulfill its electron valency by bonding with other elements, that it is literally rusting our planet into its solid form.
Wow.
From the iron-rich soil deep in the Earth's crust to the bauxite mountains, oxygen is constantly grabbing onto raw metals and locking them down into stable ores.
So it's an ongoing planetary-scale chemical reaction.
Yeah. So the next time you look around the room you're sitting in right now, I want you to really ponder what you're seeing. That solid rock on your desk, the clear glass in your window, the painted walls, the concrete foundation beneath your feet. How much of your physical reality is just oxygen, holding tightly onto another element in a desperate, billions of years old chemical embrace?
Because once you view the world through the lens of those hidden bonds, you realize that nothing is as simple as it seems.
Not even a rock.
Right. That rock isn't just a rock. It's a violent chemical reaction frozen in time. Thanks for joining us on this deep dive. We'll see you next time.